So we're going to go into derivatives for exponentials and logarithms. We alluded a little bit before that we have the derivative for natural log of x. Do we remember what that is? 1 over x, nice simple one, right? We'll explain where that comes from here. And then we also have the derivative of e to the x. We alluded to that before. Derivative of e to the x is e to the x. So we're going to try to prove where both those came from. We're going to prove it from a general form. So in other words, instead of it being natural log, we're going to do it for any log. Instead of it being with e to the x, we're going to do anything to the x. And then once we've got that, we should have every basic derivative shortcut that you will need for this class. I mean, at that point, we'll have explored polynomials, compositions, quotients, products, trigonometrics, exponentials, logarithmics. I think the only thing that we would need to explore after that is inverses. And we've hit on pretty much everything you've covered in algebra or trig. So let's begin jumping on in. This is what you got so far, right? So you need to have this memorized. Yeah, right. But thankfully, it's not about trying to memorize it from the symbols, it's trying to memorize it from the story. If you try to memorize it from the symbols, good luck and Godspeed, because I got no idea. Like, I have to figure them out from their symbols, right? Especially this one. This one right here, this one is difficult for me to write with its symbols. I have to do it in stages, right? Anybody recognize what that formula is for? That's for chain rule. So I remember chain rule as being those bicycle wheels that are all connected. So the way that I work through that one is I've got the U wheel attached to the X wheel, and then we had the Y wheel attached to the U wheel. And so I translate that and I say dy du must be the derivative of y times the derivative of u. And then I say, well, what is y? Y is the outermost wheel. So then I backtrack that a little bit and I start making it be derivatives of f's and derivatives of g's. And from there, I begin connecting it in that derivative of g is g prime, and derivative of f with respect to u is the derivative of f in terms of u, and the derivative of f in terms of u would be the derivative of f in terms of u, where u is that middle wheel. Right, so the symbols are not always the best way to begin these stories. I think that you can get the exact same amount of credit and in fact get through every single problem with that, right? That at the very beginning, that works out just as well. It reminds us we need to figure out the inner functions, the outer functions, the derivatives of them, do a little mise en place, mixing, matching. Like we've got everything we need from that earlier form. So again, let the stories carry you. If you need to make a connection, you can, but most of the time you don't have to start with these. These are just there as one way of capturing the story. Okay. I don't have up here derivative of secant, cosecant, cotangent, tangent, y. Yeah, we don't need to memorize those, right? We just figure them out in combination with sines and cosines and the derivative shortcuts. In fact, if you really want to talk about what you need to memorize, you also don't need to memorize that one. Why don't we need to memorize that one? Say a little louder. Multiplication. How did we figure? So that's the, what rule is that one? That's a quotient rule. How did we derive it? We didn't do it from the multiplication. Or at least not only the multiplication. We did with chain rule, where we raised it to that -1 power, right? Right, derivative or doing division is the same thing as raising something to a negative exponent. So you can like completely not have to worry about that one. and instead just memorize that any fraction can be rewritten as, sure enough, multiplication and a chain rule where I have multiplication by something with a negative exponent. So like you can start to parse this down and then build it back up. But again, like quotient rule is pretty easy to remember because it has that limerick that goes along with it. And chain rule will start to flow with a little bit of practice. So we talked about this one here. Let's just do a little bit of a reiteration. If I'm trying to do the derivative of f and it comes out to be 1 over x, the question is, what is f? We might think that this is something that has to do with power rule, because sure enough, it looks like something that is power rule. It looks like I do the derivative of f, and I get something with a power. Because had I done the derivative of x to the negative first, I would have got -1 times x to the negative second. And then if I got the derivative of that, I would have had x to the negative third times some constant, et cetera, et cetera. So it looks like it should be emerging from the power rule, but there's nothing above it. We could say, let's do the derivative of x to the 0. Well, x to the 0 is a constant function that just has a domain restriction at 0. And the derivative of a constant function would be 0. So this thing's derivative is 0 so long as x isn't 0. Like that didn't work. That didn't complete the chain. And similarly, if we try looking at this from integration going up backwards, like that doesn't complete the chain either. Like I can't go up one level from it and find something that makes sense. I can't go down one level and find something that I can easily backtrack. Like it doesn't work. Now we explored that this actually emerges from the derivative of natural log of x. I did not formally prove that. We're going to formally prove it today. But it is very, very interesting that all of a sudden at this stage, that power pattern kind of breaks. And that we need to consider that there is a place where I don't just continue to change exponents, that I really do hit a barrier if I follow that story and formula directly. So we want to see where that comes from and prove it. I want to talk a little bit about logarithms. I think that in algebra class, people don't have enough exposure to what logarithms are as a story. And as a result, when I say logarithms, a lot of people are like, oh my golly, those things, I don't know what they are. Like, let's just do a little bit of recap. Logarithms are a lot easier than I think we give them credit for. This is going to be just a demonstration. Don't take this literally until the end, and then you'll understand why I'm demonstrating with things that are a little less formal to begin with. Let's just do an experimentation. Let's imagine that I come up with a brand new function. I'm going to call it a fake logarithm, or a phlogarithm, if you will. Here's what the phlogarithm does. Super easy. If I have a number that goes 1 and a bunch of zeros, it counts the zeros. Cool. Right? So if I say, what's the phlogarithm of 1,000? It's 3, because I have 3 zeros. We all good on that? And if I say, what's the phlogarithm of 1,000,000, it's going to be 6, because I have 6 zeros, right? We all feeling like this is some of the easiest math we've done in a while. Good, that's what I want to hear. Now, you can also think of this phlogarithm as a power finder function. Okay, so here's what I mean by that. Power finder function. If I rewrite this and I say that I want to find the power that turns 10 into 1,000, what would that power be? 3, right? Because 10 times 10 would be 100, times 10 would be 1,000. So the power I find is 3. And similarly, if I say I want to find the power that turns 10 into 1,000,000, are we all on board that that power would be 6? 10 to the 6th is 1,000,000. With those two analogies, the bottom one being the more formal and the top one being the less formal, they're all you need to understand logarithms in their entirety. Let's take a look at some examples. Let's bounce around the room quickly. What is the phlogarithm of 100? Let me see a hand. Yeah, good. 2. Logarithm of 10. Somebody else? 1. Logarithm 1, somebody else. How many zeros do you see? You see 0, 0. So there you go. Let's double check this from a power finder style. If I say that I want to find the power that turns 10 into 100, that power is going to be 2. 10 squared is 100, we all agree? And if I say I want to find the power that turns 10 into 10, that would be 1. And if I say I want to find the power with my power finder function that turns 10 into 1, that power would be 0, because 10 to the 0th power would be 1, right? We all see the parallel. Let's keep extrapolating this. Again, different people than responded the first time. I'm going to add in a little bit of challenge here. So now I'm going to start to challenge and extrapolate the pattern. Now I'm going to say, what would be a reasonable extension if all of a sudden I'm not making it so nice? Let's start with the one on the bottom. I've got, what is the logarithm of 0.1? I'm going to see a different hand, because we've got now the logarithm of 100 was 2, because I had 2 zeros after the 1, and 10 had 1, because I had 1 0 after the 1, and then 1 was 0, because I had 0 zeros after the 1, and I want to know about, what about 0.1? Orlando, take it. -1, how come? We could look at it through the power finder, or we could kind of look at it as a pattern and say, I don't have zeros after anymore, now I have zeros before, right? So either one of those was just fine. So sure enough, we could say this is going to be -1, because again, we have finding a power that turns 10 into 0.1. That would be -1. 10 to the -1st is a 10th. That's 0.1. Good to go. Here becomes the fun one. Somebody else. What about the logarithm of 20? What's a reasonable guess that kind of continues and builds on this pattern? So tell me where you're getting the 1/2 from. You do 10 times 2, that would be 20, right? But I need to figure out how many 10 times of 10, right? What would it be? Maybe. How about like this? Logarithm of 10 was, logarithm of 100 is, logarithm of 20 should be between there, right? What's a good guess for that then? And it's got a 3/2, 3/2, right? 1.5 is? Do we all see that 1.5 is just something reasonable in that range that will continue the pattern? But at the same point, wouldn't it be a little bit closer to the 1 than to the 2? Because 20 isn't that much bigger than 10. And it's pretty still far away from the 100, right? So maybe not 1.5. 1.5 would put us right in the middle. What would be an adjustment for it? One and a fourth, 1.25, somewhere around there? Okay, sure, right? Decent guess, right? Somewhere in between here. Here's how we can double check it. Logarithms, as I have been giving them to you, this idea of finding a power or determining numbers of zeros, are literally logarithms. This whole thing has been logarithms. It's just logarithms base 10, because I've been trying to figure out how do I turn 10 into these numbers. So here's a way that we can double check it. We can say this should go along with find the power that turns 10 into what? 20. We did not use a calculator, but let's use a calculator now. Let's pull out a calculator. You all tell me what log base 10 of 20 is. Was it? 1.3. 1.3? We get a confirmation with that? James, how do you feel? Does that look like it's reasonable and supports the pattern that we found? Do we all see that that's what we're talking about here? Like, it's the idea of saying how many magnitudes of 10 do I have, because I'm trying to find the power that turns 10 into that 20. It's not quite 1, because that would have left me at 10. It's not quite 2, that would have brought me to 100. It's somewhere between 1 and 2, closer to the 1. That's logarithms. Logarithms are power finder functions. That's all they do. Now, if you want to talk about what is it in terms of other bases, I think that it's a fantastic opportunity to recognize that culturally, ours is not the only culture that can do mathematics, right? For example, in our culture, we count in tens, right? There are 10 different digits on this keyboard in front of me. Why do we count in tens? Think about it. How do we teach children to count? With our fingers. There we go. That makes sense why we count in tens, right? Would it surprise you that there are cultures that count differently? There are cultures that count in 20s. Why do you think they count in 20s? Fingers and toes, very nice, right? There are cultures that count in 60s, right? And here's how you can do it. You all can do this exercise with me. We're going to take both our hands. On one hand, we're going to use our thumb to count up our knuckles. We're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and we're going to hold up one finger on the other hand. So I've got one big group of 12, and then I continue to do that until I have 5 groups of 12. That makes 60. You ever wonder why there are 60 seconds in a minute? That seems like a weird number. Didn't we create the clock? Wouldn't it have been so much easier if we had made it 100 seconds in a minute, right? And then we could have made it 100 minutes in an hour. And then we could have figured out how many hours that leaves left in a day, right? Like we could have built a clock with a different number system. And in fact, that's what happened. The culture, right? The ancient Arabic people were counting in base 6 or in base 12, which is why there are 12 groups of seconds in certain amounts of minutes and 12 groups of minutes in hours, and why there's 2 chunks of 12 hours in a day. On top of that, did you ever wonder why in our language we have the word 11 instead of 1-teen? That seems weird, right? We've got 3-teen, 14, 5-teen, 16, 17, but then we have 11 and 12. Why 12? Because our language originates from a Germanic origin that counted in 12s. So they had different names for the 12 numbers because they were different numbers. And then once all of a sudden we started to become a culture that counted in tens, we started to express 12s in terms of these keys on my keyboard, but we still had the names from the language. So we have different cultures that count differently. So for example, if we want to talk about log base 2, we would be interacting with a culture that counts in 2s. In other words, they count in binary, like computers. If you ask any person who's familiar with binary how to express 16, this is how you express 16 in computer language, 1, 0, 0, 0, 0. How many zeros do we see there? So it makes sense that log base 2 of 16 is 4, because I'm counting the zeros, right? Not because I'm looking for zeros in 16, but in terms of I'm looking for zeros in that culture's description, right? I'm looking for the magnitudes of that base. So logarithms just tell us magnitudes. They tell us the power that we're trying to find in terms of that culture's counting system. So let's go back to that idea of it being the base 12. Who can explain now why log base 12 of 1,728 is 3? Yeah. Check it. Somebody else, while we're checking that, give me another reason this would make sense. Where are the zeros here? There are, just not in our culture, right? In their culture, there would be 3 zeros, right? Because for every single 0, this would be counting in 12s. That would be the 1s place. In our culture, the next thing would be the 10s place, right? But in their culture, that would be the 12s place. In our culture, the next thing would be the 100th place. In their culture, it would be the 144th place, right? 12 groups of 12. And then the next one would be whatever 12 times 144 is, right? The 12 to the 3rds place. Adam, what did you get when you got 1,728? So logarithms count magnitudes. They're power finder functions. If you think of them in terms of that, all the rest of this flows. Right? Here's how I can make that nice and easy for you. Let's look at some of the properties that y'all were probably told to memorize in algebra, right? Like this one here. Let's look at this one from a not trying to memorize storyline. If I did just some simple numbers, like I wanted to look at the logarithm of 1,000 divided by 100. We could simplify 1,000 over 100. That would be what? 10. And then the number of zeros in 10 would be 1, right? Now, tell me how you simplified that. Yeah. You crossed off the zeros. You literally took away magnitudes when you did it, right? So what you're saying is you took the number of zeros in the 1,000 and you took away the number of zeros in the 100, right? So what you did is you did the number of zeros in the 1,000 and took away the number of zeros in the 100. That's that formula. Does it make sense that if we divide numbers, they remove magnitudes of multiplication? I would think so. That's how we simplify division and multiplication all the time. Does it now make sense why if I'm subtracting on the inside, it's not okay to do division on the outside, right? What I mean is, is that true? Logarithm of, well, what's 1,000 minus 100? 900. It's going to have magnitude that is close to 3, right? Because it's close to 1,000 that has magnitude 3. Is that the same thing as dividing the number of zeros in each one? Nowhere close. Complete butchering of the storyline, right? 3 zeros divided by 2 zeros is saying I have 1.5 zeros in 900? Definitely not. I definitely have more than that. I have at least 2, right? So it's this idea of saying now we don't have to memorize so much. We can just figure it out from the stories. That was true. What about this one? Logarithm base c of a to the b power is b times log base c of a. Do me a favor, try this in terms of logarithms and choose some easy numbers. Work with the person next to you, see if you can come up for a reason as to why this is true or not. Go ahead and give it a couple minutes. Go ahead. Partner up and discuss. That might be a decent setup for anybody looking for a decent place to start. All right, who feels like they got an idea? Yeah, what do you got, Shamar?
10 to the power 10.
Okay.
10.
So log base what? If you wanted to just be log 10, that's totally fine. I'm just specifying if it's specifically you're looking at log base 10. It could be any base, just like that log base 2 was counting in binary, or log base 12 is counting in that culture. So you're saying log of 10 to the power of 10. That got you 10.
10 times log to the power 10. 10 times log to 10.
Like that?
Yes.
Okay, walk me through why that makes sense. Walking through step by step. What's log going to do? Well, it's going to count the magnitudes, right? Count the zeros.
Yeah.
So let's see if we can bounce it around. We'll build on your example. Go ahead, Miguel. So you're kind of saying that there's a little bit of a parallel with exponents. Let's try building up from the power finder or the counting of zeros story. Go ahead.
So 10 to the 10 power.
10 zeros. So we all see 10 zeros. That's going to 10 to the 10th power would be whatever that number is, 10 zeros, right? Okay, keep going.
So logarithm of 10, 1, and then times 10 is 10.
So it's 10 times the number of zeros that appear in 110 is the number of zeros that would appear in 10 tens multiplied together. That seems pretty consistent, right? In fact, if I look at the one at the bottom, 10 to the third is going to be how many zeros? 3 zeros. Isn't that 3 times as many zeros as there are in a single 10? Because I multiplied 3 of them together, right? There we go. Don't got to memorize a darn thing, right? Exponents repeatedly bring in magnitudes. So however much your exponent is going to be how many times of that magnitude you have. That's where it literally comes from, where I have the exponent times the magnitude of the thing I'm repeating, right? Because that's what I'm doing. I'm repeatedly multiplying and repeatedly gathering those magnitudes. True. Try this one, y'all. Give it some numbers. Tackle it from the logarithm, tackle it from the magnitudes. Try dodging the exponents argument for right now, unless you can do it through the power finder function story, just because we haven't technically proven that they are connected to exponents except with that story. So those are the two different setups that I've given you from my storyline analogy. Anybody got an ability to explain one of them? Good. Two magnitudes of 10, right? Okay, good. There it is. Do you all see on the bottom, there's half as many zeros, right? Log base 100 of 10 says how many zeros or how many magnitudes of 100 are in 10? Well, there's half a magnitude because there's half as many zeros. Let's try this from a power finder. Maybe the power finder analogy is a little easier for this one. Let's find the power that turns 10 into 100. That power is going to be 2. Give me a nod or thumbs up from everybody if we're feeling good that 10 with the power of 2 gives me 100. All right, I've only got about a half people. Let's try this here. If I say that find the power that turns 10 into 100, that power is 2. Give me some thumbs up, thumbs sideways, thumbs down if we're all on board with that. All right, great. If I now say find the power that turns 100 into 10, that power would be a half. Why a half? Because a half power means square root, doesn't it? So this idea of if I change my perspective in terms of what I'm building up to, then that means that I have to flip the magnitude, the power, because I'm scaling up by double or bringing down by half. So we've got this ability of being able to say that if you flip your base with your argument, you are reciprocating the power. You're looking at 1/2, whereas originally you were looking at double. Any questions on these before we go on? Please. Yeah. 2 is equal to 1 over 1/2.
Yeah.
There you go. Now, of course, it's not just from the logarithms of simple numbers, and it's not just from the power finders that we have on the board, but it's just a matter of saying, once we have one piece of understanding, does it make sense for everything? Does it make sense that in another culture, if I'm counting in 12s, that if I build up from a base of 12 to some number, that'd be the same thing as starting with that number and doing a root back to 12? Yeah, because that's what happens if I repeatedly multiply versus I try to undo repeated multiplication, is that I root. For the other one, if I was dividing magnitudes, does it make sense that even in a base 14 system, that if I repeatedly have a number of 14s in something and I divide some of those 14s away, that I have decreased the magnitudes? Yeah, that's how we bring magnitudes down as we do the division. So that makes sense for the original problem when we had the subtraction and the division. So all these get generalized through their storyline. So logarithms are power finder functions, or you can loosely think of them as finding the zeros if we're talking nice numbers and in a certain culture's perspective. That's why I usually stick with the power finder analogy. I find it to be a little bit easier. Okay? Any questions? Are we feeling a lot better about logarithms than maybe we did when we came in? Okay, cool. By the way, logarithms come up a lot in the real world. Here are some applications. Earthquakes. The Richter scale is logarithmic. So if I say there's a magnitude 7 earthquake versus a magnitude 6 earthquake, and I let you know that that base is in base 10, how much bigger is the magnitude 7 versus the magnitude 6? 10 times, right? Because it has one more magnitude of 10 for everyone. That means that you could have 10 magnitude 6 earthquakes hit a city in order for it to be the same as one magnitude 7 earthquake hit, right? Having one step on the Richter scale is a big deal. It's a big step, right? And it's bigger if you say magnitude 6 versus magnitude 7 versus magnitude 3 and magnitude 4. Magnitude 3 would be about 1,000, right? Units. Magnitude 4 would be about 10,000 units. That's an increase of 9,000. You go to 6 and 7, now you're talking about 1 million versus 10 million. That's an increase of 9 million units. Like, it's bigger the higher you go on that scale. Also, decibel, the decibel range, that's logarithmic. For all you chemistry people, the pH scale is logarithmic. Getting closer to a pH value of 1 requires more and more acidity than if you go from 7 to 6. Right? If I have that right. I forget if acids are the small numbers. I'm not a chemistry major, but I think they are. Right? And then there's more on top of that. I think it's the decibels, and we all know scientific notation, right? Scientific notation, that ability of saying if I have a number like 6.022 times 10 to the 23rd, how many zeros is that? That's 23 zeros, right? Like, it's a big deal if you change that exponent. All right. So now we want to start to explore these two. I'm going to go through these real fast. You are not going to have time to take notes on this, except to write yourself little bits of description for certain things that you think you will forget. So this is, again, a reminder that I've got all of this in the guided notes, that the expectation is you're printing off the guided notes, and I leave that margin blank in the guided notes so that you can just simply add little details to it, not have to copy down the length of the proof. My job here is to just make sure that you all understand that you can approach that proof and understand where it comes from. I don't need you all to like write it down. It's all over the internet and it's all over our Blackboard. So I just want to make sure that we understand where it comes from. So feel free to interrupt with any questions as far as why it works, but do your best to take notes that you can then copy into the guided notes that explain the proof as is already written. Okay? So we're going to look at the derivative, right? Derivative starts with what? The limit definition. If we're talking about formally defining something and I don't already have a shortcut for it, we do it from the limit definition. So here's the limit definition. I'm again going to use the h goes to 0 version. And so we're going to plug in x plus h into our function. We're going to plug in x into our function. We're going to set it up and begin. Now, if I already start with as it is written here, what do we see as a shortcut for logarithms that I can take advantage of? Because it kind of goes back to that power finder analogy, right? That if I'm subtracting magnitudes, what's the way that we cancel out magnitudes? We cancel magnitudes with division. That's how we remove zeros, right? Is that we divide 1,000 by 100, or we divide 1,000 by 10. We remove zeros. So sure enough, we can make this a division statement. So let's make it a division statement. It helps to know that we are trying to pursue making this in terms of natural logs and exponents, specifically with the base of e. So we're going to try to start to massage this so that it exposes to us the structure and the definition of e, or natural logarithms. Well, we can already start to see something here. Remember that e, just so that we all remember what we're pursuing here, e is defined as the limit as n goes to infinity of 1 plus 1 over n to the n. Are we starting to see in the inside argument for the logarithm that it kind of resembles that? I mean, I've at least got some addition and I've got some fractions. I'm missing the 1 explicitly and I'm missing an exponent, but I've got a little bit of something there. We're just going to massage it so the rest of it happens. Well, thankfully, I've got it divided by h here. I can write that as a multiplication by 1 over h. Do we feel good on that? Instead of x plus h divided by x, now we made it x over x plus h over x. X over x is 1. We're starting to reveal that 1. And then sure enough, we're going to get that 1 over h in as the exponent. Starting to look a lot better like our definition for e. E is the limit as n goes to infinity of 1 plus 1 over n to the n. Looking close. The challenge is that right now, well, a couple of different things. One, I don't have a limit going to infinity. I have a limit going to 0. That's about as different as you can be. However, if h goes small, that makes this fraction small, right? In the same way that if n goes big, it makes this fraction small. So the fractions are both becoming small. That's some good agreement. What about the exponents? As n gets big, the exponent gets big. As h gets small, the exponent gets big, right? 1 over small becomes big. So we've got this structure that is good behind the scenes, just not explicit with the notation. The fraction's getting small, the exponent's getting big in both cases. We just need to find a way of making that be straightforward. So what we can do is we can say, let's let 1 over n be the fraction I want h over x to look like. And so a little bit of rearranging here is going to say that n is x over h or any combination thereof. I'm going to essentially relabel everything so that it starts to more closely resemble e. So we'll let n be x over h, and if we do that, notice what emerges. It's almost exactly that definition of e. That's great. Also, I can even replace the limit notation because, as we said, h going small was the same thing as that fraction going big, so I can restructure everything and say n going big and h going small, same meaning, different appearance. I'll pause here for a moment. Are there any questions on where I lost anybody? We're not done yet, but this is a long proof. Okay, so now we're just going to try to make this a little bit more explicit. So we want to make it so it just looks like that definition of E. So let's go ahead and take that 1 over x exponent here. And let's bring it out in front. Now I've got very explicitly that structure for E. Any questions here on how I did that or why? The same idea as reverse, right? Where we said things being multiplied can get brought in as exponents. Things in exponents can be brought down as multiplication. So that's all we're doing. Well, now I've got log base b of E. That doesn't sound right. We're more used to saying log base E of something, right? So I need to be able to flip that base with the argument. And we explored that property. If I flip the base in the argument, I just need to make it a reciprocal, right? So I can do that. Notice that to flip the arguments, I make it a reciprocal. So I'll make it a reciprocal. Log base E is what? What's a nicer word for log base E? Natural log. Let me get our final form. So what that means now is that if I want to do the derivative of log base 2 of x, that would be 1 over x times natural log of 2. Nice, quick, straightforward. Not too difficult a formula. Notice it resembles the 1 over x that we expected to get if I did the derivative of natural log, right? In fact, let's explore that. Let's do the derivative of natural log of x. Derivative of natural log of x is the same thing as the derivative of log base e of x, which I can then use my shortcut to say that is 1 over x times the natural log of the base. Natural log of e is 1, and we're left with our missing bit. So do we need to memorize the derivative of natural log? You could, or you can memorize this form, and this form is the derivative of any log. More powerful. All right, give me some thumbs up, thumbs down, thumbs sideways as far as if we go back into the guided notes and we look at this proof, we could be able to explain to ourselves where it comes from and why it made sense. All right, good, because that's really what this should be, is an ability to go back and to kind of reiterate when we're not so pressured for time. All right, let's take a look at this technique, because now we need to do the derivative for exponentials, and this one is a fun one to pursue. First, as Michaela kind of helped us recognize, logarithms are power finder functions. That means that they just undo exponentials, right? Let's look at this from a story. B to the x equals y. Is that the same thing as saying I want to find the power that turns b into y, and that power is x, right? X is the power that turns b into y, that grows my base into a certain argument through magnitudes, right? So what we're going to do is, before we start to analyze the exponential one directly, we can make it in terms of logarithms, and we already know the derivatives for logarithms. We just did it. Saves us from having to go all the way back to the limit definition, although you can do that too. It's just much, much, much more difficult. So that means that if I want to do the derivative of one side, I could just do the derivative of the other. Well, let's think this one through. Derivative of x with respect to x would be 1, right? Power rule for there, right? 1 comes down, decrease the power, and or it's linear, and the slope of a line of y equals x, the slope is, with enthusiasm from all y'all, what's the slope of a graph of y equals x? 1, so that'd be the derivative of 1, right? Derivative is 1. So this side is going to become 1. For the other side, I've got to do the derivative of a logarithm. Thankfully, we have a shortcut for that. But notice, there's a hidden chain rule. I'm changing x, x changes y changes log of y, right? As I change x, y changes. As y changes, log changes. That means x does not change log of y, x changes y, and through y changes log of y. There's a series, a ripple, a chain of events here. So we've got to use chain rule. We've got to recognize that there are layers, that x goes to y, but y goes to log base b of y, which is our u wheel. 3 wheels. Well, if you do the derivative of one of them, we've got a shortcut for that. What's the derivative of y and x? I have no idea. There's nothing that connects those directly in this formula. But thankfully, I can do a little bit of rearranging and say, let's just move it so the dy dx is alone and replace y back, and we've got our final structure. There's a process called implicit differentiation. We're going to cover it a little bit more on Friday, but it's the idea of saying I can do derivatives wherever they appear in a formula. I just have to make sure that if I'm ever having a mismatch between x and y, that I count that that's one wheel in the chain rule. So for our last little bit, if I wanted to say what's the derivative of e to the x, that's the same thing as using this structure. Natural log of the base times e to the base. And we're back to what we knew before. That's all I got for you. If you have any questions on this, let me know. But make sure that you take time soon to capture what we went through today and put it in the guided notes. That stuff's going to leak out of your brain really, really quick. Capture it before you forget.